Hello my dear friends. This particular screen is the title screen associated with our first video lecture on basic electronics. The subject code is 18ELN24, which is there for second semester first year students. Module number 1 entitled Semiconductor Diodes and Applications, and this is lesson number 1. Myself, Dr. Mahendra M. Dikshit, Associate Professor, Department of E&CE, KLS VDIT Haryal, would like to present my views on this particular topic entitled Basic Electronics. This is the content for today's video lecture. We will have to understand the basic requirement of today's video lecture, which I call it as prerequisites for the present video lecture. Topics to be covered in this session are in detail mentioned. Course learning objectives have been listed, and then actual body of lecture that is to be covered in this particular present video session will be summarized there along with the final summary of the present lecture. Few concluding remarks and other necessary details such as applications, significance and importance of today's topic, few assignment questions and few additional references. And of course we will end up our lecture session by representing the Bloom's taxonomy levels for this session. The prerequisites for the present video lecture, since we are dealing with the fundamentals of semiconductor devices, we need to have proper knowledge of physics, and of course few definitions such as atoms, molecules, proton which are positively charged, electron which are negatively charged, neutron which has got neutral charge, and then basic semiconductor lattice structure, especially dealing with the semiconductor lattice structure, classification of material. To certain extent we must have these 4 points as minimum prerequisites for this particular session. Then the topics that will be covered in this section, I mentioned it as level 2 because we need to understand them. Topics to be covered in this session are nothing but definition of valence, forbidden and conduction bands, which are there for the classification of materials based on energy band diagram. Then the types of semiconductors, especially intrinsic semiconductors and extrinsic semiconductors. Currents that are present in semiconductors such as diffusion and drift currents. And of course we will list some of the course learning objectives in which students are able to understand basics of semiconductor physics, to learn classification of materials based on the energy bands, to study the fundamentals of semiconductor materials, and to understand the important currents in the semiconductor materials, which further help us in understanding the device physics. Let's try to move on. Few of the definitions such as valence band and the conduction band and the forbidden band. These statements are not written by me. These are referenced from some of the very renowned reference materials. So hence the valence band is defined to have the flow of electrons within the atoms in a fixed energy levels. However, the energy of such electron in the inner shell is very superior to the outer shell of electrons. Of course, the electrons which are present within the outer shell are named as valence electrons, and these electrons include sequence of energy levels which form the energy band named as valence band, and this band includes the maximum occupied energy. So this is also one of the important aspects that we should understand before we proceed ahead with the energy band diagram. Moving on to the forbidden band. This particular forbidden band gap is nothing but it is the gap which is the conduction band and the valence band certainly incur in between, and of course this band is forbidden one with no energy presence. Therefore there is no electron flow in this particular. And of course the conduction band, it is nothing but the valence electrons which are attached loosely towards the nucleus at room temperature, and some of such electrons from valence electrons will leave the band freely. So they are called free electrons because they flow toward the neighboring atoms. These free electrons will conduct the flow of current within the conductor, which is nothing but the conduction of electrons, and the band which includes these electrons is named as conduction band. these are also very essential with respect to the conduction band. So let me try to show you some of the GIF information so that you can really understand what it is being done with respect to valence band electrons and then how they jump towards conduction band. You can see there are electrons which are situated at valence band. When you try to impart sufficient amount of energy, or if you want to apply some amount of external voltage, they will move from valence band to conduction band and they become free. It depends upon the amount of energy that we supply to these valence electrons, which can jump from valence band to conduction band through a small gap which is called as forbidden band gap. And this figure is illustrated with the caption demo of electron flow from valence band to conduction band, which is taken from reference number 1. So this is one of the important definition and the illustration that students should understand before they study the electron current in semiconductor devices. The next aspect in our lecture is nothing but the classification of materials based on the energy band diagram. The classification of materials is basically done in 3 categories. The first category is insulator, the second category is semiconductors, and the third category is conductors. And the figure that is illustrated here, which is nothing but classification of materials, is taken from reference number 2. And firstly it illustrates the insulators as one of the classification of materials based on the energy band. That is nothing but there is a huge band gap that exists between the valence band and conduction band. Hence the electron, even in spite of applying the sufficient energy, they do not cross this forbidden band and reach the conduction band. Hence the forbidden band gap is very huge, and hence this particular type of material is called as insulators. Insulators are useful in most of the electronic applications in device manufacturing and so on. The second classification is semiconductors, whose conductivity lies between insulator and conductor. That's why the name is entitled as semiconductors. In semiconductors, there is a small amount of band gap exists between the valence band and the conduction band. Upon supplying sufficient amount of energy to valence electrons, they jump from valence band to conduction band and they become free. This is how the conduction in the semiconductors takes place, and hence it is called as semiconductors. Then the third classification is nothing but conductors. Of course, there is very less, or there is no separation, that is forbidden band gap is present between valence band and conduction band. They are very near by each other, and hence easily electron can travel from valence band to electron and valence band to conduction band, and they become free, and hence the conduction is possible in conductors. Of course, the application of semiconductors in most of the electronic devices, it is basically used, and the electronic industry very heavily depends upon the manufacturing of semiconductors and applying those using those semiconductors in day-to-day regular electronic device manufacturing. It is preferred, and conductors are nothing but these conductors are useful in almost all electrical connections, even the connections between the semiconductor devices, so on and so forth. It is basically useful. Then moving on to the types of semiconductors, which is also very essential for our study, is nothing but it is classified in 2 ways. The first one is called as intrinsic type of semiconductor, and the second one is called as extrinsic type of semiconductor. Intrinsic type of semiconductor, it is nothing but it is available in purest form, and in fact intrinsic type of semiconductor, in valence band the number of electrons that are present will always be equal to number of holes. So these are some of the properties which I wish to share amongst all the students fraternity. Is nothing but in intrinsic semiconductor, especially in valence band, the number of electrons will be always equal to number of holes. And of course, these intrinsic semiconductors possess very low conductivity, hence they are not preferred to be used in the construction of semiconductor devices. They are not at all used in the construction of the semiconductor devices. This must be underlined. And to get rid of this practical circumstance, what we prefer extrinsic semiconductors. The intrinsic semiconductors can be converted into extrinsic semiconductors by adding several levels of impurities, and adding the impurities to the intrinsic type of semiconductors is known as the process of doping. And by using this process doping, we can definitely make the semiconductor conductive, which can be under controlled conductivity theory. And by doping, the conductivity in extrinsic semiconductors can be controlled, and hence they are preferred over intrinsic semiconductors in the manufacturing of electronic devices. Again, these extrinsic semiconductors are subclassified into two types. The first one is P-type semiconductor, and the second one is called as N-type semiconductors. Some of the properties associated with these two types of semiconductor materials belonging to extrinsic semiconductors. In P-type, in fact, the third group element of the periodic table is added as a doping element, which provides extra holes, later which can be called as the acceptor atoms. And the example for such impurity is nothing but the chemical compound aluminum, gallium, which will have trivalent impurities. And of course, the majority charge carriers in P-type are holes, and they move from higher to lower potential in P-type. And one more important information is nothing but minority charge carriers, which are electrons in P-type semiconductor materials. Similarly, in N-type semiconductor materials, fifth group element is the doping element, which can provide extra electrons, later which can be called as donor atoms. The example for such a trivalent, pentavalent impurity are nothing but the chemical compound arsenic and antimony. The majority charge carriers which are present with this N-type semiconductors are electrons, and of course they always move in opposite direction to the holes, and hence they move from lower to the higher potential in N-type. And one more added information here is nothing but the minority charge carriers in N-type semiconductor, which belong to extrinsic type semiconductors, are nothing but the holes. So this is one small comparison between P-type and N-type of semiconductors, which can give us opportunity to understand these details once again when we try to study p-n junction diode. So moving on to the next concept, that is nothing but current in semiconductors. We know that there are two different types of currents in semiconductors. As a prerequisite also these are understandable, but as a very prime concepts in our semiconductor diodes and applications, it is important to understand once again the diffusion as a part of module. So I'll be explaining you what do you mean by diffusion current. That is the first type of current. And the second type of current is nothing but the drift current. So let us concentrate on diffusion current. Here there is one semiconductor material kept under test, which is in short it is called as SUT, semiconductor under test. And one of the important aspect associated with this semiconductor kept under test is nothing but it is having a non-uniform charge carrier concentration. Let it be a conductor or semiconductor, our example explanation will hold good for diffusion current. So as I mentioned, to understand the diffusion current, there is a semiconductor under test, SUT, and which has got non-uniform charge carrier concentration. At this end of the semiconductor, the charge carrier concentration is high, and as you move towards the other side of the semiconductor material, the charge carrier concentration is reduced. As a result of which, and as a result of the force of repulsion, the movement of electrons or the electrons that are situated at a high charge carrier concentration area tend to get diffused into the other side of the semiconductor material, that is where the low charge carrier concentration is present, and hence the movement of such electrons from high charge carrier charge carrier concentration area to low charge carrier concentration area will constitute a current, which is in turn called as the diffusion current. Figure number 4 illustrates the demonstration of the diffusion current in semiconductor, and it is also observed through this particular graphical interchange file, that is nothing but the GIF file, wherein the charge carrier concentration is changed from high to low from this end to the other end, as a result of which the electrons tend to get diffused from high charge carrier concentration area to the low charge carrier concentration area. It is as depicted in the total figure that is represented in figure number 4, demonstration of diffusion. Few more additional points which are related to the concept of diffusion current are listed for your reference. Diffusion current is a current in a semiconductor which is caused by diffusion of charge carriers, holes or electrons, and this current is there which is because of the transport of charges because of non-uniform concentration. And of course, one important aspect is nothing but diffusion current exists in the absence of difference between the diffusion current that we have seen with respect to this drift current. The second type of current that we would like to see here is nothing but the drift current. You can see once again the semiconductor material is kept under test, but the difference that you find here is we are going to apply the external supply voltage, supply of voltage to this semiconductor diode. And one thing that we should remember here is nothing but in semiconductor, whenever there is a application of external voltage, the number of electrons will always be generated excess in number with respect to the number of holes in the semiconductor devices. So as a result of which the number of electrons will get the number of holes wherein the current is generated in the circuit, and excess number of electrons will tend to get drifted in the device, and hence this movement of drifting of electrons will lead to the current called as drifting current, and this drifting current will come out of the circuit, come out of the device and move towards the positive terminal of the battery. So one thing we must remember here is nothing but the conventional current which starts flowing from positive end of the battery through the device till the negative end of the battery, which we call it as conventional forward current direction, is always in opposite direction to the flow of the drifting of electrons. And the drift current, as I mentioned, it is always flowing opposite to the flow of the conventional current. Figure number 5 demonstrate the concept of drift current in semiconductors, which is taken from reference number 5. Few more additional points for our reference. Drift current is nothing but it is an electric current or movement of charge carriers which is due to the applied electric field or due to electromotive force over a given distance. A current is produced due to the flow of charge carriers. The drift velocity is the average velocity of the charge carriers in the drift current. And of course, as I mentioned, conventional current always flow in the opposite direction of the drifting electrons. And one more important understanding that we should understand here is nothing but the drift current exists only when the external voltage is applied. So you can always compare and contrast the drift current in comparison with the diffusion current. Moving on to the concluding remarks session for the video lecture, that is nothing but the course outcome. However, this is a very short version of video session, but it is going to give you some of the basic additional prerequisite for the study of the module, and hence I have made it very brief. And the possible course outcomes for the students is nothing but they can understand the basics of semiconductor theory, classification of materials based on the energy bands, which is very essential, classification of semiconductor, and why to prefer extrinsic semiconductor or intrinsic type is also one of the important outcome while they are studying. And of course that could be one of the course outcome. They will come to know that the extrinsic semiconductors are far suitable than the intrinsic semiconductor because of the controlled conductivity concept in the extrinsic semiconductor. The concept of currents in the semiconductors, most of the students will directly concentrate on PN junction diode and the theory later on. But before that, there are two important types of currents such as diffusion and drift current, which must be understood, and of course that should be one of the course objective as well as course outcome. So I listed in both the categories. Some of the applications is nothing but understanding the basic principles of semiconductor theory, help in studying the coming specific topics of PN junction diode, and of course different types of currents assist us to better understand the forthcoming concepts of the module. Some of the assignment questions I have given for students so that they can understand how the questions can be framed, how the answers can be made, or probably how the answers can be attempted with the required details as I mentioned in my presentation. So before I conclude, let me present you the additional references I have used here for my presentation. Of course, these are additional references to the module number 1. However, some of the references textbooks have been already mentioned in the lecture notes and of course in the syllabus copy. And it is also important to represent the Bloom's taxonomy levels for this session. So I have taken 6 level Bloom's taxonomy diagram, wherein today's lecture is only concentrating for 2 levels, that is nothing but level 1 and level 2. And of course level 1 I have decided to have the prerequisites because it is only about remembering the previous concepts. So hence I decide that the level 1 will be listed towards the prerequisites, and of course level 2 is all about understanding the concepts. So without understanding the concepts we cannot further proceed ahead with these several other levels. Our video lectures presently being shared is basically concentrating on definitions, materials, classifications, and basic concepts associated with the currents in the semiconductors. I can list them as level 2. So these are the 2 levels which can be used for the present lecture session, which can be helpful in representing the Bloom's taxonomy levels related to the course. So before I conclude, I would like to acknowledge the following people. That is, first of all, I would like to thank the management of Karnataka Law Society, VDIT Haliyad, for providing us a kind support. I would like to thank our beloved principal sir, Dr. Vadiraj V. Katti sir, for providing academical ambience, timely support and suggestions to incorporate and to enhance the teaching learning process as KLS at KLS VDIT Haliyad. I would like to thank our HOD, faculty members and non-teaching staff, and last but not the least our student fraternity, without whom I think the sharing of the resources in this form wouldn't have been possible. For further details, I think students can contact. Thank you.